Welcome to our latest edition of CSM Explained. My name is Timo Eich. I am Business Development Manager at CSM, and today we are once again talking about an exciting topic. It's about the testing of fuel cell drives on test benches and in road testing. If we would go on the street and ask people about their imagination of electromobility, most of them would probably have battery electric vehicles in their mind's eye. And that makes sense because many people drive to work in the morning and back home in the evening, usually within a manageable radius. And in the evening at home, you can easily hook up a battery electric vehicle to a wall box and recharge it, and perhaps coupled with a photovoltaic system. Now, there are also areas of mobility that depend on covering long distances without recharging or refueling. Think of the transportation sector, freight transportation, for instance. For short distances, battery electric concepts make a lot of sense here too, keyword last mile. But for the long haul, when you want to be able to cover hundreds of kilometers at a time, most purely battery electric drive concepts are still severely limited in terms of range. And that is largely due to the overall concept of the purely battery electric drive, because longer ranges would require even larger batteries, which in turn would add much more weight to the vehicle and thus reduce the range. This is therefore a fundamental problem inherent in battery electric drive systems. Fortunately, there is a drive concept that can play to its strengths in precisely this area, the long haul, and that is the fuel cell drive. Here you can see an example of a truck with a fuel cell electric drive. However, it could just as easily be a boat, a train, or an airplane with a fuel cell drive. And especially in the development phase of such a drive, we now have to carry out a wide range of measurements in order to optimally adjust the control and the regulation of the drive. On the one hand, this requires measurements directly at the fuel cell drive. The fuel cell itself is an electrochemical reactor that generates electrical energy from the supplied hydrogen and atmospheric oxygen in what is called the cold combustion. And one fuel cell then generates a voltage of above 1 volt. And in order to harness this energy for propulsion, we naturally need a much higher voltage. That's why we simply take many of these fuel cells, connect them in series and stack them. And this is then called a fuel cell stack. And the fuel cell stack, of course, needs other components to form a functioning fuel cell drive. We need media supply, we need a cooling system, and we need an electric system. At the same time, this fuel cell drive is only one part of the entire powertrain, and so it is almost important to determine how the fuel cell drive behaves in the entire powertrain. And for this purpose, the energy flows between the components, the motors, the converters, inverters, the high HV storage system, must be investigated, particularly in the road test, in order to be able to examine all the environmental influences as realistically as possible. And how exactly to do these examinations, this is what we are now looking at together. If we now take a look at the relevant measured variables for the fuel cell drive, we are of course interested in electrical measurements like current and voltage, for example the stack voltage of the fuel cell stack. In addition, however, the developers are interested in completely different measured variables such as flow rates, pressures, humidity, and of course temperatures. And it is precisely these thermal and mechanical measured variables that are highly relevant for the investigation of the fuel cell drive. Because to ensure that this cold combustion process runs optimally, the fuel cell stack must be precisely adjusted and readjusted at all times. And that's not that easy because in real life, a vehicle is exposed to a wide variety of environmental influences such as heat, cold, moist air, dry air, vibration, and so on. And this is exactly what makes the optimal media supply and conditioning of the fuel cell stack very challenging. What's more, the fuel cell drive is governed by a control unit, and of course we also want to record the control unit's measurement data simultaneously with the analog measurement variables. And now there are two major challenges. First, since we want to be able to establish causal relationships between the various components, thus corresponding measurement data must be acquired simultaneously from the various components. And now it's extremely important that they are acquired exactly synchronously. This is particularly important for the very fast signals of voltage and current, but also for the ECU data. And secondly, many of these measurement signals must be recorded at high voltage potential. And in particular, the physical signals from the fuel cell drive. This means that we need a way to acquire the sensors used there in a high voltage safe manner. And how to meet these challenges, what options are available for this? We are now looking at this step by step for all parts of the fuel cell drive. And for this, let's take a look at a simple schematic of the fuel cell stack. In electrochemical terms, the stack consists of an anode system, a cathode system, and the membrane in the middle between them. In the anode path, we are now dealing with the hydrogen supply. This means that hydrogen is now fed to the fuel cell stack from hydrogen tanks via pipes. And to ensure that this takes place at exactly the right rate, a recirculation blower and a hydrogen gas injector ensure that exactly the right amount of hydrogen is fed to the fuel cell stack. If we now want to investigate the hydrogen supply, then it is primarily flow rates and pressures that need to be measured. And by means of this measurement data, we can work out and control the optimum dosage of hydrogen for the fuel cell stack for a wide variety of operating points. And you could now use our proven standard measurement technology for various sensor types. These are our CSM mini modules with CAN output. And to these modules, you now connect your flow rate sensors and pressure sensors. What has proven itself for more than 20 years is our concept to collect all measurement data from analog sensors as close to the sensor as possible, digitize it directly on site, and then transmit it by a secure bus system. Because with such short analog sensor lines, we naturally limit external interference to a minimum, and in this way have high quality measurement data available. Now let's take a look at the cathode path, where the fuel cell stack is supplied with atmospheric oxygen from the ambient air. Here we have an electric air compressor as an essential component. There could also be a passive humidifier, for example. And here is an essential difference to the anode system. In most fuel cell drives, we are already dealing with high voltage in the cathode path, meaning voltages above 60 volts. This is because the electric air compressor is usually already operated at high voltage. So we measure flow rates here, we measure humidity, we measure pressure, because here the developers want to see exactly what the air supply is like, which has to be set precisely for optimal operation of the fuel cell stack. And humidity is particularly important issue here because the fuel cell stack is fed with oxygen from the ambient air. And here we now have the most diverse scenarios that have been to be taken into account. How does the air influence the cold start behavior of the stack? How the warm-up phase? And how various other operating points? How is the air moderated in winter when it's cold and the air is particularly dry? What happens when the air is particularly humid? All this has to be considered and investigated. But the essential point is we must now carry out these measurements here in the cathode system in a high voltage safe manner. And for this, we need high voltage safe measurement technology and a high voltage safety concept. This high voltage safety concept consists, amongst other things, of electrically insulated touch-proof cables with a very special structure that varies depending on the measured variable to be recorded. Then it also includes special high voltage safe and mechanically protected connectors. We see them here. And the core of this high voltage safety concept is a high voltage isolation barrier which must be provided for each measuring channel and which provides reinforced insulation according to DIN EN 61010. If you want to know more about this, just have another look in the first episode of CSM Explained in our archive on our website. And with measuring modules protected in such a way as there are our high voltage safe measurement modules for voltages and active sensors, we now reliably record standard sensors for flow rates, humidity and pressures on high voltage potential. And these modules provide our active sensors with a sensor supply voltage and measure the values at the same time, and both in a high voltage safe manner. Now, the cold combustion also relies on optimum temperature control. And to ensure this optimal temperature control, the fuel cell stack needs a cooling system. This cooling system usually also includes a heater, and this heater, as well as the rest of the cooling system, is usually also operated with high voltage. In the cooling system, developers are logically mainly interested in temperatures and also humidity. Above all, the temperature and the humidity must be optimally set in the fuel cell stack so that it delivers maximum output, maximum energy. And this is only possible if the thermal management of the fuel cell drive works in the best possible way and regulates the cooling circuits in an optimal manner. Since we are working here in the cooling system with high voltages, the temperatures now also must be recorded in a high voltage safe way, and this of course requires high voltage safe temperature measurement technology. And for this purpose, you could now use our high voltage safe temperature measurement technology. These modules are available for thermocouples, PT100, PT1000 resistance sensors, and also for special applications with high precision digital temperature ICs. And with these measuring modules, you now measure your temperatures in a high voltage safe manner and directly send the measured data on the CAN bus. Now we come to the electrical system of the fuel cell drive, the so-called high voltage path. And here we now see a power distribution unit, a PDU, and we see gray and orange lines here. The gray line represents low voltage, less than 60 volts for the anode system, and the orange lines represent high voltages, in our case here now 400 volts DC. Here the developers want to measure currents and voltages to find out how they behave in the various operating phases, what energy consumption, for example, air compressors, circulation fans, and the heating of the cooling systems have. And above all, what happens when these components are switched on or off, because it is precisely here that transients and harmonics can occur in the electrical system, which must be determined and investigated. For functional tests, we then also want to measure, for example, voltage and current at the output of the fuel cell drive to determine its power output. For this purpose, we have to install suitable sensors, particularly for the current measurement in the various electrical paths. And for the low voltage range, for example, in the anode path, we have various options here, such as ring current transformers, These are our CSM lamp sensor packages here in the picture, or we use current clamps like the CSM current clamp system, or we directly measure in the line with a current measuring resistor, a shunt, such as the CSM shunt here in the picture. And you select these depending on the application, measurement range, dynamic range requirements, and available installation space. And you now simply connect all these sensor packages, for example, to our fast EtherCAT measuring modules. They acquire the current values very dynamically with up to 1 megahertz per channel, because the transients and harmonics are usually very fast processes which we have to sample accordingly with high sampling rates. And because of the high sampling rates and the correspondingly large amount of data, these modules no longer communicate via CAN bus, but with a fast bus system, the EtherCAT. And for the electrical measurements in the high voltage paths, we now of course also need a dynamic high voltage safe current and voltage measurement. And that's what we do here with our HV breakout modules. With these high voltage breakout modules, we can now very dynamically record high voltages and high currents simultaneously, and both signals fully synchronously in one single measuring device. And for this, the HVBM, as we call it, is directly inserted into the high voltage cables. So we disconnect the cables and feed them into our HVBM via cable clamps and connect them there. Or we use the power lock plug system, a quick coupling system for high voltage signals. The huge advantage is we do not need analog signal lines because we digitize the measured values directly on the spot. As a result, the measurement signals have the best possible quality. Our HVBM measures the inner conductor current of up to 1000 amps by means of a fully temperature compensated shunt module, and simultaneously and fully synchronously the voltage of up to 2000 volts. And with a special variant of the HVBM, we could even simultaneously determine the shield currents on the high voltage cables. The HVBM samples current and voltage at up to 1 megahertz per measuring channel, and these fast signals are then sent on the CAN bus. At the same time, the HVBM also has a CAN bus connection, for example, for the transmission of averaged measurement data in endurance testing. The great thing is now that our HVBM can directly calculate various parameters from current and voltage on board, such as RMS values, active, reactive, apparent power, and the power factor, and then make these available as virtual as calculated channels. And this is what built-in single-phase measuring HVBMs look like. Here in the cathode path between PDU and air compressor, the HVBM now measures the power consumption and the on-off behavior of the air compressor, as well as its influence on the entire electrical systems of the fuel cell drive. And the HVBM here on the right is now measuring the total power output of the fuel cell drive during a functional test. Here we see once again the complete fuel cell drive and the various measurement applications at a glance. Pressure and flow rates in the anode path at low voltage potential, in the cathode path flow rates and humidity at high voltage potential, in the cooling system humidity and especially temperatures at high voltage potential, and in the electrical system voltages, currents in the high voltage path. Now let's take the fuel cell drive out of the picture just for a moment. And if you remember how we started, one of our challenges was the synchronous and simultaneous data acquisition of all the different measured variables at the different paths. And this synchronization and bundling of the data streams from various measuring devices is what we are now doing with our XCP gateway. this is the module here on the top. This XCP gateway is a data concentrator that on the one hand collects the data of all connected fast EtherCAT measurement modules. It has up to 4 EtherCAT connections for this purpose. And in addition, it also collects all measurement data from the CAN bus connected measurement modules. Now our XCP gateway synchronizes all data streams with better than 1 microsecond jitter and then forwards the measurement data via XCP on Ethernet to the measurement computer or data logger. And for synchronous networking with other fast measurement technology, the XCP gateway is also equipped with PTP. We will come to this back later. And this is how our data streams would then look like. The slower measurement technology is connected to the XCP gateway via the CAN bus here in blue, and the fast measurement modules via EtherCAT here in green. And with that, we have acquired all measurement variables, both high voltage safe on demand and synchronously in the fuel cell drive. Now we come to the electric powertrain, because there's a lot to measure here as well. Essentially, here we want to measure voltage and current, and related to that, of course, electrical power. And here too, we have two main requirements. Namely, on the one hand, we need 100% synchronous data acquisition of the various measured variables, and on the other hand, we need high voltage safe measurement technology, since we now for sure have to deal with high voltage potentials here. Let's take a look at a simple schematic of a typical fuel cell electric drivetrain. So on the left side, we are now come from the fuel cell drive here on the left, from the electrical output and with 400 volts DC. And the first thing we see here then is typically a DC-DC converter. Next, we have a high voltage power distribution unit, our PDU, and now we have two paths here. At the top, we now see the connection for the PDU to the inverter, which turns the DC voltage into a three-phase AC voltage for our electric motor. And at the bottom, we see our high voltage traction battery. Our developers are now interested in the energy flows between all of the components of the electric powertrain, and so they want to measure voltage and current at various points between the components. For example, between the PDU and the inverter, between the PDU and the battery, and between the inverter and the electric motor. And now we can investigate, amongst other things, voltage ripples in the DC circuit. We can determine efficiencies, for example, the efficiency of the inverter, and we can examine the entire system in various operating states. And for this purpose, we again take our high voltage breakout modules and insert them directly into the high voltage cables between the individual components in order to record voltage and current complete synchronously and high voltage safely. The one-phase HVBM here for the DC measurements, you already know from the measurements on the fuel cell drive. But here, between motor and inverter, we now see yet another variant of the HVBM. And this is the HVBM 3.3 for three-phase measurements of currents and voltages. This device now measures the free currents in and the free voltages between the phases with up to 2 MHz sampling rate per measurement channel. Of course, this produces a lot of measurement data, and that is the reason why our HVBM then sends the data directly on XCP on Ethernet to the measuring computer or the data logger. But the HVBM 3.3 can do even more, because it now also has XCP gateway functionality at the same time. And this means that we can now connect further EtherCAT and CAN measurement modules to the HVBM 3.3, and thus the HVBM 3.3 then functions as a data concentrator just like the XCP gateway. And the HBM 3.3 is also PTP capable, meaning it can be synchronized with further fast measurement technology. And here we see now how the one-phase HBMs from the DC measurements are connected in series via Ethercat to the XCP gateway port of the HBM 3.3. So if we now look at the entire powertrain, it looks like this. We have the entire fuel cell drive with its instrumentation on the left, and we have the electrified powertrain with its instrumentation on the right. Now we bring all the measurement data streams together at one point at our measuring computer via XCP on Ethernet. These are the plaque lines here from our XCP gateway and from our HBM 3.3 with the XCP gateway function, which now converge here at our measuring computer. And so that the data can now also be properly recorded and also, for example, immediately analyzed online, we need appropriate data acquisition software. And this software comes here in our example from our partner Vector Informatik and is called vMeasure. vMeasure is the little brother of CAN-AP, so to speak. This is a software you may already know from your practice. Both software packages are very powerful, equipped with multi-threading functionality, offer extensive visualization options for the measurement signals, and above all, are capable of handling a large number of fast measuring channels. Because if you now generate data from CSM modules, vehicle buses, ECUs, video, and so on, if you generate that much data, then you need high performance software for data acquisition and especially also for online calculation. And a special feature here is the e-mobility analyzer function package for real-time analysis of voltages and currents and for determining key figures of electrical power such as efficiencies. Here we have once again an overview of the entire instrumented fuel cell electric powertrain, and now we come to a final extension of this setup because almost all of the powertrain components also have a control unit that generates measurement data. And one of the main tasks in the development is to optimally adjust these control units. For a better view, we will remove almost all components from our picture and now only see the fuel cell stack, the DC-DC boost converter, and the PDU of the powertrain. And these are, of course, all regulated and controlled by means of ECUs. Now, in order to check whether they are doing this optimally, the measurement data of the ECUs must be recorded in parallel, simultaneously, and also 100% synchronously with the analog measurement data. And it is usually the case in these tests that the developers also want to make changes to the settings of the ECUs during the test and calibrate them. And for this purpose, Vector Informatik offers suitable interfaces for measuring and adjusting ECUs, which then have direct access to the data streams of the ECUs via the so-called plug-on device interface, also called POD here. These are the Vector VX interfaces, which we now see here and here. And if we now take a look again at our measurement network, we see that the VX interfaces now also transmit their measurement data to the measuring computer via XCP on Ethernet, the plaque lines, if you remember. And thus now all fast interfaces are doing so. These are in our example here, the VX interfaces, the XCP gateway, and the HBM 3.3 with XCP gateway functionality. And to ensure now that all these interfaces acquire their measurement data 100% synchronously, they are synchronized using PTP, the precision time protocol. This is a standard synchronizing mechanism according to IEEE 1588 for synchronization with better than 1 microsecond accuracy. And that way, all our measurement data from the analog measurement technology and the ECUs run together here on our measurement computer and are displayed there by our data acquisition software, stored, and if we want it, already analyzed online. Here you can see an overview of our complete measurement setup. And this is exactly how a full-scale test of both the fuel cell drive and the complete powertrain, including the digital measurement data of the ECUs, can be carried out. And all of what you have just seen is part of the Vector CSM e-mobility measurement system. We have recorded and processed analog measurement variables with the components of the e-mobility basic measurement system and the ECU data with the vector interfaces. And there's one last thing that we have not addressed yet, because instead of a measuring computer, we can also perform the complete data acquisition by means of a smart logger of the Vector VP series. And this is then a perfect solution for the road test if you do not want, or are not allowed to take a measuring computer with you into the vehicle. This means that all these tools are ideally suited for both road tests and test bench applications, and thus these tools accompany you in every step in the complete development process, starting with component tests and system tests in development, to endurance tests on the test bench and in road trials, through to approval and functional tests and end-of-line tests in the production. Because as a rule, more or less the same parameters always have to be measured and determined in all these development steps. And this makes the Vector CSM e-mobility measurement systems your powerful and reliable companion for fuel testing of fuel cell drives on the test bench and in road tests.